All right, let's see how quickly I can teach you about optic stuff. All right, first basic one is, so V equals F lambda is for waves, right? So light, that V is C. If that's, so that C is the speed of light in a vacuum, right? So let's say we have two different materials. We have light coming in here, and N is, of course, the index of refraction. Sometimes it's called optical density. But the index of refraction of a vacuum is 1, okay? And all other n's are greater than 1. The speed of light in a material is c divided by n. So I just said that n's greater than 1, so you can see that, of course, that the light in any material is going to be less. And when it moves from one medium to another, and when we measure this, we measure angles from something called the normal, and that's the line that's 90 degrees to the boundary, right? So if it has an incoming, so incident angle of theta, we know that light, when it hits a boundary, will reflect, and that angle of reflection is equal to the angle of incidence. And then if this is a different medium, we know that the speed is going to change because it has a different n. And because the speed changes, and this is called refraction, because the speed changes, the light will bend, so that, and you can think about it like as an army, like a line of army people coming in. You can think about, here, let me change to a different color. This is better. You got, these are the wave fronts, and they hit this, and then if they slow down, I can't draw, guys. The wave fronts are always perpendicular to these, and if it slows down, it's kind of like the army guys going through mud. Like when you start looking at refraction, you'll see that mentioned a lot. But anyway, speed changes, the frequency stays the same, and so lambda changes, and it'll change the same way that V does, okay? So this is called refraction, and the relationship between, this is called, the relationship between these angles and the indices of refraction is called Snell's law. Oops, Snell's law. So that definitely comes up sometimes. Okay. This bending of light, so I didn't actually write the word here. This is called refraction, and so this is when you look in, in a glass of water with a straw in it, and the straw looks bent. That is because of refraction, and so sometimes they use the word apparent depth to talk about, where it looks like it is versus where it actually is, right? Because it looks like it's in a different place. Okay. So refraction and reflection are definitely important in optics. So we have mirrors, right, which that's reflection, and lenses bend the light, right? So that's refraction, right? So mirrors, so a lot of times talk about a mirror, and then there is the radius of curvature. So this would be a concave mirror. And so the idea here is that if you put an object right here, and you say, oh, if light, let's make light yellow, won't that be fun? Yay! If light comes in here, then where it gets reflected for mirrors is through something called the focus. and the focus is half the radius of curvature. So it does this. Okay. The other thing that happens is that if light goes through the center of curvature, then it comes straight back. Okay. And this place where it just appeared, where that little intersection appeared, that is where your image is. So in this case, the image, so this distance is the distance of the image. That is the distance of the object, and 1 over the distance of the object plus 1 over the distance of the image is 1 over the focal length. So when you look at this picture, this blue image right here is inverted. And you see that there's actually light going through that point. And so therefore it is a real image. So when images are formed on our retina, actual light hits our retina, and what actually appears on our retina is an inverted image. And that our brain is nice and it turns it the other way around for us. But inverted always goes with real, and then virtual always goes with upright. So let me show you a ray diagram for that one. So in this case, we've got a convex mirror. Here's our object. Here's our radius of curvature. Here's our f. Remember, f is r over 2. So let's get some light colors. So here's what happens. This light gets reflected, but so remember, if it goes in parallel, it goes through the focus. Well, actually light doesn't go behind a mirror, right? So what it does is it gets reflected along the same line as if it went through the focus, okay? And then the other thing that the other ray that you use for convex mirrors is one that goes right here, and then it just comes off like, oh God, that's a horrible picture. That's supposed to be the same angle, like on top and on bottom, but I think you get it. But so that's what that does. But then you trace it back, and then lo and behold, what is that intersection? Where is it? There it is. So this is a virtual upright image, okay? You will notice that it is smaller. So if you want to think about something like a magnification, which you could imagine being defined as the image height divided by the object height, that is equal to negative the distance image, and then that's di, and that's do. There's a negative here because this image distance is actually negative, and the magnification will be positive here, and that's how you know that it is upright. So there's lots of fun negative stuff. I doubt they're going to have you do that kind of thing, but I think, so that's with mirrors. You get similar experiences with lenses. So as you can see, when you look at a lens like this is called a convex lens, and so there's a center on each side and a focus on each side, right? The center for this one is over here. The center for this one is over here. So there's your focus. There's your focus. So if the light comes in here, it'll go there. Oh, sorry. There was obviously an object here. I'm trying to do it really fast. It'll go straight through the center. There's your intersection point. So, you can play with a lot of these. I doubt in science full they're going to have you do things like that. But I'm just trying to sort of throw some stuff down. As you can tell, this image that is formed here, actual light goes through it, and so that means it's real and it's inverted. So you literally always get real and inverted together, virtual and upright together. Okay, and so now here I'm just going to throw down some real quick resistor, capacitor in series and parallel. Okay. Resistor series. So R1, R2 equals some kind of R equivalent. So resistor series, R equivalent is just the sum. Resistors in parallel, where you have this is sum R equivalent. That's the inverse crap. 1 over R1 plus 1 over R2 is 1 over R equivalent. So what you get real used to real quick for parallel calculations is if these are the same, then it's R over 2, okay? Right, because you get 1 over R plus 1 over R, you get 2 over R is R equivalent. So R equivalent is R over 2. If you have 3 of the same resistors, then the equivalence is R over 3. So hopefully that's the kind of thing that they would have you do. If it's like 2 and 4, that's also a kind of thing that they might have you do. So 1 over 2 plus 1 over 4. So 4 is 2 plus 1. So our equivalent here is 4/3. It's always smaller than either of them. So the equivalent resistance in parallel, so maybe that's worth a whole nother slide. In parallel is less than each resistor. The equivalent resistance in series is greater than each resistor, okay? Capacitors in series is 1 over C1 plus 1 over C2. And caps in parallel are when you add them. While we're looking at these equations, springs are like capacitors. So springs in series are the inverse. And springs in parallel, you add them. Okay, hopefully that's a little bit that'll help.